I want to know how wrong I am. The extent of what's going to happen.
Howdy, Bert. Sorry, I got a little bit of coffee in here. And it just spilled on the way in. And Kian, name, is that you? Maybe. Stags or Stomps? Sorry. Here, I'm good. Sorry, I got a little coffee. I think the rest just take yours and that's I don't, I think the average is like 4.5, but I'm not absolutely sure. You got a bunch of 10s, but you had a bunch of low grades. And I think a lot of people, they probably felt a little clumsy with a quarter grade, but it was one of the problems we did in class. Now, here's what I'm going to do today. The solutions are up for that. And what I'm going to do is actually, I'm going to try to show you how to work the very problem you did on your quiz with a Smith chart, okay? Now, that's the thing. It's obviously you have an interest, and you'll see how you do. And well, this is going to be painful, but I'll try. Oh yeah. Sorry. Hey, I want to tell you this too. All right. Now, I dropped the lowest quiz. So if you bombed one, learn from it, and realize it gets harder from it. There's going to be more difficult material coming up. But you can't get behind. This stuff will compound on you, it'll destroy you if you're not careful. So where's the clip with it? No, not this again. He took the clip. Tell you what. Can you figure out a way to get a clip or something on that thing so I can use it? You got a paper clip or anything? Oh wait, here it is.
There's a Band-Aid.
I got it. Sorry. You know, this microphone is not treated. I've had nothing but trouble with it. All right.
What kind of class is this?
Oh, this is circuits.
What is this? Did I put this up?
No, I was looking at my canvas. I was looking at my grades. I was like, what class is this?
You never got rid of it. You have to make it. Yeah.
You were like, did I miss a class?
I was like, damn, it's a good grade. Best grade I got right now.
But I did a lot of work that weekend.
This thing works. I don't have time for it. Just read it.
Yeah, someone take this.
All right, so class, I want to show you how to do this with a Smith chart. And hopefully you can follow me. Now, I could start with a blank Smith chart. Matter of fact, let me do that. And I'll try to do this. And by the way, I printed out, if you're going to, you know that Smith chart I sent you? The one that said good one? If you print it out full scale, or have it no scaling, because it scales it down by 90%. This is thank you. This is a full-size picture.
Thanks, Preston.
Things to go with time, I hope.
What in the world?
Can you hear me? Is this all right? All right, class, I'm going to do this. I thought about what to do. This is probably the single best way to teach you Smith charts. And hopefully I can do it. All right, this is a Smith chart, and you all have one in front of you, right? How many looked at the videos or other materials? There's a lot of information out there. The main thing is you have to have a good Smith chart in order to read what's going on. So with a Smith chart, the first thing you have to understand is this is simply a polar plot of the reflection coefficient. That's all it is. And if you think about any point on here, it will be the magnitude of the reflection coefficient we measure down here, and you'll see this in a second, and the angle. You can get the angle up here. And I'll try to do this in a way that you understand. All right, so first, let's go through this. If we're talking about the problem on the quiz, the load impedance, I believe, was it equal to 60 plus J40 ohms. Is that right, class? Just tell me if I'm wrong. All right, now, the first step, if you're using a Smith chart to do this, is find a normalized load impedance. And that's capital ZL over Z naught. I hope you can see this. So what is that going to be? Well, that's going to be 60 plus J40 over 50. The characteristic impedance is 50. So that's 1.2 plus J 0.8. Do you all agree with that, everyone? Just take a moment, make sure you can see what I'm doing and understand. How many see this? Y'all understand? All right, the next step is plotting this on a Smith chart. I like to use pencils here. And I thought there would be some pencils. I don't know if this works. Well, if you don't have a pencil, you use a pen. All right. Unfortunately, this is a thick felt tip. All right, so here's the one circle. Now you see right here where it says 1. Can you all see that? Thank you. This is the one circle. This is the circle, the real part of a normalized impedance that would be plotted here. Can you see how this goes all the way around here? And it would be just at a radial distance called 1. The center is right about here. Can you all see that? All right, that's the real part. So that's the one circle. We need a real part of 1.2, correct, class? Now please watch this. Well, this is 1. As the circles get smaller, do you see 1.2 there? Take a look at your Smith chart. Make sure you can see 1.2. And far back, can you see it, guys? Anybody not see it? That's the I use the term trajectory, but that is on this circle right here. This is a circle that's symmetric about the actual, I call it the equator there. We know that's our real part. Now our imaginary part is 0.8. Do you all see that? J 0.8? Right? All right. Now all these values here, where they, this is 0.8. That's actually J 0.8. Where the trajectories intersect the circle normally, the outer circle. These are all imaginary values. And label this, they're all plus J on the northern hemisphere, and they're all minus J values that intersect down here. So then follow this trajectory in if you can. I'm not doing this very well, but if you follow it in, you can see where 1.2 hits J 0.8. Can you all see this? This would be the point right here, and it's called ZL, and that's 1.2 plus J 0.8. You all follow me in that, class? How many see this? All right, next, take a straight edge. All right. I'm using a ruler. Anything with a good straight edge. I actually like these flat plastic drawing tools that they have. Anything like this that you can actually get a straight edge, and then go from the very center. See, it says 1 in the center there. Can you all see that? And draw a line and go. And we're going to go all the way through this. Unfortunately, this isn't plain. Give me 1 second. Just go right through the point that I hit, which is over here. Now, I'm not going to be able to do this that well here. This thing's a little curved, right? And draw a line straight through both sides. Now that's supposedly a line straight through, but it's just not working too well today. Y'all know what I'm up to, right? I'm trying to get through that point. Gosh. Like that. Y'all follow me, class? Get them through both sides. Just take a moment and do that. I'm really trying to make sure. Hopefully you have, does anybody not have a Smith chart? Okay. And now that you've done that, the next thing you do is take your compass. Get a good compass. Don't go the cheap on this stuff. I know people get these like, I don't know, 50-cent compasses or something. Those things can do more damage because they'll open up as you go ahead and do a spiral. This is a drawn tool. This is a real one. All right, it's basically locked at the radius. Take that and take the actual stabbing point and put it at the center of the circle and take this part. And if you can't see it, yell at me, but I'm trying to show you what I'm doing here is I'm gonna go and make a circle. First I'm gonna get the point, the line there where it's 1.2 plus j.8, the normalized impedance, and just draw a circle all the way around it. Now this is not exactly what I was hoping for, but I'll do what I, man, everything's going on. It's one of those Mondays. Let's see if I can get that better now. All right, now let me try it. Can you all see what I'm doing here? I'm just making a circle centered at the origin that goes through that point. Can you all follow me? Please do that. When you do it, don't adjust your compass. Leave it where it is. Now, how many do it have this done? Can y'all, did you get it back there or not? You okay? Some people aren't going to do it, but it's helpful if you do it. And I'll tell you why. There's a little subtleties that you don't realize. Like these things, especially cheap compasses like she has, they'll open up as you spin. This
isn't even mine.
Look, you got one too, right? Let me just show you something.
That's just the pencil sharpness. It's hard to.
Yeah, and here's what happens. See how this thing flares? This is actually pretty stiff right here. But I promise you, on quick, especially a final exam,
Yeah.
I'll see people that rip one off from their roommates or something to use, and geesh, and everything's wrong. And they said, well, it was the company. No, it's your fault. I told you to get it one. You didn't. All right. Anyway, I'm trying to help you. Now, take this. Can you all see this? Take this measurement and come down here. Now, will you see it says reflection coefficient E or I right here? Can you see that? What I'm showing you? It's this point right here. I'm trying to make sure it's right here. It's the bottom one on this Smith chart. Do you all see it? They might be at different points, but E is the symbol for voltage in the old British system. It was electricity, and I was current. All right, so if you look there and take this, now it's important you do this right, and take the stabbing in and put it at the center here, and then do this point that I've got right here, that I'm going to use this blue marker to show you, that is the magnitude of the reflection coefficient. Take a look at it. It's about 3.52, 3.52, something like that. Anybody know exactly what it is? Because I don't. 0.352? Is that right? Can you show him, sir? Sir, do you know how to do it? Show him. Just show him. Get up and show him. I'll tell you, anybody not see this? Because if you can't see it, just raise your hand. Believe me, everybody has, especially if you don't have good eyes, they have trouble seeing it. You see it?
Yeah, but you know, I got point 4. I got point 4. Funny part is this isn't even my point.
I want it back.
Yeah, now I got it.
That's my fault. All right. Anybody not see it? It should be at 3.52. Remember, the measurement starts at the center there, right at the middle of the paper, and you move over. One thing I'll see people measuring from the edge over, and they get the wrong value. Do you all see this, class? Do you see it now? Anybody not see it? Okay. Now, that's the magnitude. Here's how you get the angle. You can do this with your calculator. But if you look up here, and this is not, gosh, I didn't do this right. You see this is 50 right here? Can you see that, class? I circled it. You with me, class? Take a look. It says 50, right? Count up the striations. This is about 55 degrees. Now, it's actually, I think, a little slightly different on the quiz solutions, but it's about 55. How many see that now? So that's the magnitude and angle of the reflection coefficient using a Smith chart. Admittedly, this is a tougher one to read because it's close to the center. The closer the actual normalized impedance gets to the center, the harder it is to read these things. Everybody with me on this? Okay, now, next, after that, you got mine.
You can have it.
I hope that helped.
Thank you.
Then take this. Did you adjust it?
No.
Gosh, thank you. All right, go up to the top here, and you see it says SWR right here. Can you see that?
Where?
Oh, I'm sorry. Right here. Can you see that right there? Now take a good look. Make sure you can identify this in your Smith chart. Y'all see it down here? Everybody? Jeremiah, you guys got it? Where's Andrew Strickland? See here. He'll be my go-to guy to walk around and when things get tough. See, he's had some of this he had to draw. All right. Now, after that, you can see you can take this thing, your compass, or you could just use a ruler and estimate, but I like this because it's pretty good. It doesn't move. All right. Then take it and come here, measure from the center, like I'm doing here. You can see this, and just kind of line there. And I overestimated that. That thing opened up a little, but the actual value should get is right about here. It should be about 2.02, something like that, for the standing wave ratio. Can you all see that? Now, you don't need a Smith chart to find that out. You can get it by taking 1 plus the magnitude of the reflection coefficient, or over 1 minus the magnitude of the reflection coefficient. But they have everything here for quick calculations and estimates. Now, generally speaking, a good design will have a standing wave ratio less than 2. Closer to 1, the better. And I'll talk more about that later. Okay, now that's that. Now, the next thing we're going to talk about, so far we've got the reflection coefficient, standing wave ratio, we've got the normalized impedance. The next thing you want to get is the input impedance. Do y'all hear me? Everybody with me on this? All right. This you pay careful attention to because this is where people, they have questions and they're not even sure what to ask sometimes because this stuff is small. Now if you look here, I'm going to blow it up on purpose, hopefully. And I'm going to try to show you this. Okay. All right. I'm going to even move it this way. You see it says wavelengths towards generator. Can you all see that on your Smith charts? And I'm going to roll it back the other way now. Try to center this. Can you all see that? Now, on the outer rim, they'll abbreviate it WTG in a lot of Smith charts, but you'll notice it's at the outer rim, right? These give you what I call mile markers. They tell you basically where you are relative to other positions. Don't worry about anything but that for now. So if you look here, where this line, here's my first point on the Smith chart, and this is messy, I'm sorry about that. If you go right through here, you're going to get something, it's about 1.7, looks like on my 1.74, but I could be wrong, 0.174 lambda. This is on the outer edge. Can you see 1.7? And just estimate. Now, mine isn't exact. I got some slop, obviously. How many can see this? Think of that like exit 51 on the highway. It's a mile marker. It's a location that is relative to other locations. Now, we are at the load, and if we want to move wavelengths towards generator, you can't see this part. There's an arrow right there that shows you the direction you move. It's clockwise. Can everybody see that? In the back there, can you all see it right here? You got it? All right. Guys over here, Jeremiah, you guys got it? You see it or not? Show him. Show him. Go ahead. You got it? All right. All right. Now, I'm going to move from here, but I'm going to move a quarter wavelength. Isn't that the length? All right, so if you add a quarter wavelength to this, what do you get? I don't know. 0.452. Isn't that right? Just add 0.25 to 0.174. Don't you get 0.452? Am I wrong? Anybody? 0.425. I'm sorry. You're going to find out it's right here. it's going to be right here. And I knew that because if you go a quarter wavelength, you go exactly halfway around this circle. So this is going to be 0.425 lambda. Just identify that point. It's on the outermost edge of the Smith chart. Just take a moment. I'm really trying to help you in the most basic way. You got it? Over here. Take a moment. I'm not rushing this part because this is where eyes have. And if you can, if you print out some of these things, I got 60 of them in the, waiting for me in the printer room that are enlarged. Yes, sir.
I was just asking, was like a quarter wavelength that we added to it, was that in the original problem?
Well, remember it was a quarter wavelength long transmission line, right? So if we're at the load, we have to move a quarter wavelength from it. How many understand that? Are you guys okay with this, guys? All right. So now, how many can see that point that I put down there, 0.425? All right, now, when you want this is a normalized input impedance. Please listen to me and make sure you see this. The normalized input impedance is right here. You're going to have a little harder time reading that. You're going to have to estimate the value, but I'm going to show you a trick too. If you want the normalized value right there, now listen to me. I was here and I had 1.2 plus j 0.8, right? Just take 1 over that and you'll get this. This will be equal to 1 over 1.2 plus j 0.8. Can somebody give me that value? I don't have it in front of me, I don't think. Is it 0.5? Maybe I do have 551 or 557? Is it 0.557? And then it's going to be minus j 0.385. And I'm sorry, it's not looking that good, but take a look at that point. Are you getting about that? And if you look at this, here's how you get it. If you come up here, boy, it should be this, about 0.557. And the imaginary part, if you come down here, now my eyes are not going to do me justice here, but it should be about minus what is it, 385, I think. Is that right? Take a moment, see if you can see that. How many can see that? All right, 1, 2. You're not able to see it? Are you guys not able to? It's going to take some time. You have to interpolate between lines. You may not. You got it? Okay. Yes, sir.
So wait, when you drew that line, is it like it doesn't matter with respect to the center?
It goes right through the center. From the center point, goes right through the center, through the. It's not drawn very. Through the point where the normalized impedance was. Goes. I just slice the thing in half. All right. That's how we got the angle for the Smith chart. All right. And if you go straight through there, that second point I showed you on the other side of the circle is just 1 over the actual normalized impedance. Now you should get. By the way, is that right? If I take 1 over 1.2 plus j 0.8, do you get that?
It's like 0.576.
576. All right. So you get minus j what?
Minus 0.3.
All right, 0.384. Anyway, you should, if looking at that correctly, you should see the real part to be that. Can you all do that, class? Admittedly, it's a little tough. In the imaginary part, you should see also. You with me? Now that is the normalized input impedance. All right. Would you do me one favor, sir? Don't get off that off your head. Can you multiply that by Z naught? Multiply it by 50 and tell me what you get. If you don't mind. Did you already knock it off?
28.84 minus 19.23.
28, I'm just going to say 28.9 plus, or minus what? Minus J what? 19? That would be an approximation of the input impedance. We moved, so anytime you're moving, now listen to me, once you go in on that reflection coefficient thing, remember everything is normalized. As you move wavelengths towards generator clockwise, doesn't matter how far you move, if you stop at a point, it'll give you the input impedance once you find the values at that point and then multiply by Z naught, because everything's normalized on these. Everybody follow me on this? How many understand that? Now, a couple things about a Smith chart that you got to understand. If I take a look at this Smith chart, one of the things that becomes apparent if you think about it every time you go around, if I started like at this point right here, and I went around the circle an entire 360 degrees, every time I move that far, or lambda over 2, I'm back at the same point. You all notice that? Matter of fact, whenever you move from a load impedance, this is for something at a constant frequency, every half wavelength you move, just basically, it's going to repeat the exact behavior every half wavelength. So from 0 to lambda over 2, all the impedances will be repeated, and the standing wave ratios and everything else from lambda over 2 to lambda. All right? Now, the bottom line on this is, so if you have a transmission line that's 1.2 lambda long, you can forget, you can subtract off half wavelengths until you get something less than a half wavelength. So if you think of it, it's 1.2 lambda, subtract off a full wavelength, I got 0.2 lambda. So if you went ahead and took your normalized impedance, plot it, you would only, and you wanted the input impedance 1.2 lambda, you'd only have to go 0.2 lambda to figure it out. Are you all with me on that, class? This is really important. This is something the book doesn't bring up real well at first, but I'm going to tell you this. Now listen carefully. These are tricks in a sense. If I'm here, right, that's where I came in at. You all with me? That's point 1. Usually I tell people, like, I've got a 1 there. Label 1, that's where you came in. You got to keep track of this stuff. Now, if I wanted to know, now listen to me, where the voltage was a maximum in terms of how far I have to go from that. When I look, I'm moving in this way. Whenever you cross this part of the equator between 1 and, this is the infinite point right here, this is where the voltage is a maximum. Can you all see this, class? Now just look at this. This would be where my Vmax is. So how far do I have to go? Here I started at 0.174. That was my mile marker where I started. You with me? How many see this right here? That's where I started. If I go and I hit here, you see the mile marker is 0.25. Can you see that? Now, how many see this right here? So if you subtract 0.25, that's where you ended up, and subtract 1.174 from it, what do you get? Somebody do that for me.
0.076.
So if you went 0.076 lambda from the load, that would be where the voltage would be a max magnitude. You all hear me? Now, where is it a minimum? Exactly a quarter wavelength from that. So if I move from here and I keep going around, where this circle intersects this part right here, that is where it's going to be a voltage minimum. I apologize for being so messy. But you all follow me on this. So if you add a quarter wavelength to that value that you gave me, was 0.07 something, right? Then you would figure out how far you have to go for a voltage minimum. Now that is, remember, the voltage is actually changing sinusoidally. It has a max, goes to a min, goes through 0, goes to another max, but the absolute minimum, and then but the overall maximum value is capped, and the minimum value capped, and these are the peaks. These are the maximum minimum values, okay? All right, now, something else about this, we'll do a few more problems, I think. If you take a look at this, I'm working from the load, and I'm getting the input impedance, I'm getting the standing wave ratio, I'm getting the deflection coefficient, and I'm getting where the voltage maximum minimum is. You all with me on this? However, I could say that I have a transmission line. Now just listen to me, and I bet you see it. And I can say, say I know the characteristic impedance of the transmission. If I measure my input impedance, I get a certain value, right? Now just think about this. Well, if you take that input impedance, I want to know what the load is. I'm after what the load value is. Well, if I take that input impedance and then normalize it by Z0 and plot that point on the Smith chart, and I wanted to know the actual load impedance, now instead of going wavelengths towards generator clockwise, I would go the other direction. I'd go wavelengths towards the actual load. Do you all follow me on that, class? Now, if you look on this Smith chart, you're going to use the same technique as I talked about. Look on this Smith chart. And I better blow it up. You see this where it says wavelengths towards load? Can you all see that right there? Take a moment. And it is a set of markings just inside. The outer circle has wavelengths towards generator. Just below that, there's a second circle that says wavelengths towards load. Can you all see that? It indicates that you're going counterclockwise. Do you all see that? So if you marked the normalized input impedance that you had and you wanted to know what the load impedance was, you would add however long the line is in wavelengths to that number, and you would go in the actually counterclockwise direction to find it. Now, here's a couple other points that are important. I'm going to get a fresh Smith chart. All right. Remember, I said anytime you go around that circle a full 360 degrees, you move half a wavelength. Y'all hear me on that, class? Now, if by chance you end up with something like, I stop at a value here, I'm going to just talk my way through it, and then I subtract, let's say it's got a mile marker, and then I subtract off wherever I stop is the point. I'd read the mile marker here if I want any kind of distance, and I subtract the mile marker here, and it's negative. Just listen to me now. Remember how I said if you add a certain amount, you get a certain amount? Well, what happens if you add a certain amount and it's greater than half wavelength or negative? Y'all follow me? You'll see this in a second. If it's greater than half wavelength, you subtract the half wavelength from that and use that as the marker point on there, the mile marker. Y'all hear me? And if it's negative, you add a half wavelength. Now we're going to do some problems. You're going to see this, and it should become apparent to you. I'm not even going to touch matching right now. But the best way to do this, in my opinion, is some problems. Now, in the book, if you look, I have to leave it upstairs. All right, so if you go to your book, go ahead. No, you, all right, I'll do it. And you know, I'll tell you one thing, that lady that I sent you the video on, how many actually looked at any of this? Now she goes super slow. At times I want to just have 1.5 the speed because sometimes I'm there. But she defines everything so clearly that you would need to know to understand a Smith chart. And she has sequential videos. I don't know how many she has on this, but she does a great job. So in the book, got some water damage.
Not me. That's scared.
Crying over something. Anyway, if you look at page 110 in the book, that says the Smith chart. So how about we do this? We do problem 2.27. I'm going to need somebody to read it.
I can do it.
By the way, I have so many coffee stains and tea stains in my books. It's an embarrassment.
Okay.
All right, so for this problem, okay, where is that? All right, this is problem, the number is
2.27.
27. This is problem 2.27. Can you see that?
No.
Oh. There we go. Hold on. Yeah, that's better. All right, 2.27. So go ahead and tell me the specifics.
All right. 0.690 lambda.
Is the length.
Yeah, long
All right.
lossless.
Yeah, it's lossless. Don't worry about that.
Z
Lossless.
naught equals 75 ohms.
So here's the deal. They've got a load here,
Yeah.
and they have ZL. And then they've got the length of the line, L is equal to 0.69 lambda, right? And then, please just follow me on this one. So they want, I think the input is here, but I'm not sure.
They want, yeah, they actually no, they want the reflection.
We'll get all that.
Yeah,
What's the
yes.
characteristic impedance of this?
It is the characteristic.
Of the lines, at 50 ohms? Anybody?
It's 75 ohms.
75?
Yeah.
75 ohms. And what is the load?
It's 15 plus J 67.
Now this is not a good one, but they want reflection
We can't
coefficient.
see.
Huh?
We can't see.
Oh yeah. All right, so I'm just showing you what's on the problem. What's the first step we do, class? Anybody? Always normalize. The very beginning. Divide that by 75. Can you tell me what that is, anyone? So what is ZL normalized? Which is ZL over Z naught. Just tell me. Oh God.
0.2 plus J 0.89.
All right. Now that's normalized, right? Do it with me, class. It'll help you. Where's 0.2? 0.2 is right here. Can you see it? Circle in blue. You all see that right there? Take a good look. That's the real part. You're on this, I call it a trajectory, on this circle for the real part. Now the imaginary part is 0.89 J, right? Can you all see this too? With me? So where's that? Well, this right here, if you go straight up, this is J1, right? Can you all see that? Where's 0.89? Well, there's 0.9. 0.89 is right about here, isn't it, class? I'm just trying to show you. So that means if I try to get this point, this would be the value of ZL normalized right here. It's going to be 0.2 plus J 0.89, and that would be your 0.1. Can you all see that? Just make sure you can. Don't assume it's too simple. Do you have a compass and stuff or not? Okay, I mean, doing it helps. I mean, if you really see it, you don't have to, but trust me on this one. These things, they're subtleties. They're small things you won't see, and if you don't do these, come quiz time, you kind of fall on your face. You don't know what to ask you. So just do them. All right, next, take your compass, and then stab the center of the circle right here, and move it out to here. Now this isn't planar, so I'm not going to get a really good circle, but it doesn't matter the order you do this. I'm going to do the circle first. All right, and then after you do the circle, take your straight edge and go from the center of the circle right through that point. This is not planar, so just bear with me, I'm trying. And you should get something like this. Leave your compass at the setting it's at. Can you all do that, class? With me? Now, I want somebody with good eyes to tell me, what are you reading there for wavelengths towards generated? I'm getting about 0.11246. It looks like that on mine. 0.11246. Is that right? Anybody confirm that? It's on the outer edge. Can you see that? Is that wrong? How many got about that? You're going to get slop. You're going to get some variation. Really sharp pencils, drafting pencils make a big difference. The finer the point, the better. And the better your eyes, the better. And the bigger the Smith chart, the better. All right, so now he says, well, let's get the reflection coefficient, standing wave ratio. You still got your compass, right? How do I get the standing wave ratio? Magnitude and the reflection coefficient. Let's get the reflection coefficient first. I go down here, that's it, right here. I stab the center. Yeah, if I can. about there. And you can see it's about, I'm getting point, what is it, 0.8 about? Can you see if that's about the magnitude you got? That's this right here. I'm getting about 0.8. Anybody? You getting about that? You see it over here? No. You guys got it? Jeremiah, you guys got it? You don't got it? Can you show them? Do you know how to get it or not?
Oh, compass.
Okay, can you go over there and show them? Just talk over it. Anybody else not see it? Because if you don't see it, I need you to see it now, in class. I don't need this to go on forever.
I'm getting about 0.82-ish.
All right,
Is yours?
and we'll go with that. But again, I admit, my method is got a lot of variation just because of the size of the pen and all this, all right? And that's not a planar thing. I can't do a really good straight edge shot. You guys got it now? Over there? We're good. Okay, now, so that's the magnitude. What's the angle of this? Now you got to go to the inside, and here's where my eyes, I see 90 here, right? So I'm getting about, was it 92, 94, 96 something degrees? It looks like it's about 96 degrees for the angle of reflection coefficient. And I'll put it down here. So I'm getting a reflection coefficient of approximately 0. I'll call it reflection coefficient of about 0.81 at an angle of call it, what is it? About 96 degrees. Take a good look. How many see this? Now, I mean, it takes some squinting. If you don't, I wish I had some stronger glasses. But you with me, everyone? All right. How do I get the standing wave ratio, anyone?
1 plus, 1 minus that.
Well, we could do that, but if we want to use what's available on the Smith chart, where do I go?
The bottom of the page.
I just go right here, don't I? I got to get from the center to right here. And this is a big one. It's like 0.9 or 9 about. Is that what you guys got? Just shy of 9? You see it, miss? You all good with this, class? Let me see this right here. All right, we've taken care of that. Now, he says, I'm going to assume something here. I'm assuming he wants the input impedance. He may not have said it yet, but if he does he? If he wants the input impedance, how do we get it? We know where ZL is. I mean, Z load is, right? Normalized? Now, we would add 0.69 lambda, but what's the key thing there? It's greater than the half wavelength. So subtract the half wavelength from that. Right? What do you get? 0.19. Is that right? Isn't it 6.9 or am I wrong? How long is it?
Like general? Like,
Is it 0.69 lambda long?
Yes, it's 0.69 lambda long.
All right, you got to subtract the half wavelength, don't you? Remember, every half wavelength that it repeats, what's that going to be? 0.19. Isn't it 0.19 lambda? Do you see it or not, sir? Yeah, I'm talking to you. Do you see it or not?
I got something different, but.
Well, subtract the half wavelength point.
Oh, you're subtracting it first? Never mind.
Yes, I'm going to subtract first.
Oh, I got it. I subtracted it.
Y'all with me? Now, we're going to move that far, but we're going to move from this point. Hear me now, class. I'm sorry if I wasn't clear. This is our mile marker. This is like mile marker 51. We have to add 0.19 lambda to that, and we're going to end up here. What is that plus 0.19 lambda? Anybody? Just do it. 0.19 is going to be point what? 3, isn't it? 0.3 what?
06.
0.306, is that right? So that's down, let's see. Gosh. 0.36 what?
That's it. 306.
0.3?
Yeah, 0.3 and then
0.306?
Yeah.
Okay. 0.306. It's about here. Now I gotta take a straight edge. Once you get there, you know, you take a straight edge, find that point, and then you gotta shoot right through the center here. And can you tell me what you read right here? I can't, I think I got a little too much slop in mine. Can you give me the normalized value of that Z point? It's about, it's close, I don't know, close to 1 it looks like. And the imaginary is about minus J point 28 maybe? Can somebody do that for me?
0.8 minus J 2.4.
All right, 0.8 minus J
2.4.
2.4? Okay. 2 point, I believe it, I believe it. So that's actually what Z in normalized is, right there. Can y'all follow me? Take a moment, make sure you see this. This is irritating sometimes because if you don't have big Smith charts or good eyes, there's small things you won't be able to see. I want to make sure you see it. In the back there, you guys see it? Over here? Guys? You see it? All right, multiply that by 75. What do you get?
60 minus J 180.
That should be Zn. Can anybody confirm what it is? Because I gave you the solutions. Anybody? Almost that. Yes? No? 75. Is it in the book or not? Yeah, I gave you solutions, right? On one number?
Yeah, you did.
It might be in the back. I don't know.
Yeah, I'm looking at it.
How many see this right here? Now let me tell you one other thing. I'm just about out of time, unfortunately. I'm going to go through this with matching and just think about this logically. If you wanted it matched, it means there's no reflection at all right? If you have a load, you know, if the standing wave ratio is not 1 or the reflection coefficient is anything but 0, some of that energy is reflected back. The way to get rid of that is we're going to move from the normalized load impedance. Just hear me now, it'll make, yes sir.
Zn was 60 minus J 180.
What did we get?
Same thing? That's right. Okay, same thing.
Okay, we got it. Good job. Anyway, so if you move, let's assume we have a load impedance like ours. If you move to where the load, if you move far enough so the real part of load impedance is just 1. It's normalized at 1. You hear me? If we could get rid of that J business, then it'd be great. You know what we can do? We can do a bunch of stuff. One is we could add a capacitor in series or an inductor in series that has the exact same reactive value to cancel of the opposite magnitude, same magnitude, opposite J sense, and can cancel it. Do y'all hear me? That's one way. That's adding a component. Second thing we could do is actually use a transmission line with a short or an open on the end and put it in series or parallel and get rid of it too. But that's the next part of this class. I'm going to give you a bunch of problems. I'm going to ask you to do them. And if on Wednesday you try and you don't understand, we'll go through them. I hope you have some better drawing and stuff like this. I like doing it on the board. Once you know how to use a Smith chart, you can tell me. Then we'll go through matching, but it will make sense. It will make sense and it won't be hard to see. All right, thank you. Sorry to keep you so long. And thank you for fixing my mic.
Preston did that.
All right, Preston, thank you. Did you understand it?
Yeah, I do have one question for you after. I just want to double check.
Come on up here, we'll hear you. We're going to have a herd come in a second. Yeah, if you got questions, come on up.
I want to be very careful. I was going to ask you. Yeah.